Welcome to another episode of the Mapscaping Podcast. My name is Daniel and this is a podcast for the geospatial community. My guest on the show today is Sandy Kennedy. Sandy is the Vice President of Innovation in Autonomy and Positioning at Hexagon. Awesome title, Sandy. And today on the podcast, we're talking about what better positioning looks like. The workings of GNSS constellations, the errors that affect GNSS positioning, and the potential solutions like Low Earth Orbit or LEO satellites. We talk about visual positioning. Sandy also touches on terrestrial-based positioning technologies. And all of this is not nearly as boring as it might sound. Firstly, because they're all really interesting subjects. And secondly, because Sandy is enthusiastic, she's incredibly knowledgeable, and just a really interesting person to talk with. Oh, by the way, if you notice a difference in the audio quality, I've just moved to New Zealand and I am still in the process of setting up my studio. Hi, Sandy. Welcome to the podcast. Oh, let me try and get your title correct. The Vice President of Innovation in Autonomy and Positioning at Hexagon. How did I do?
Pretty good. Good to talk to you today, Daniel.
Yeah, really nice to talk to you again. Really appreciate our last conversation, so I'm looking forward to this one. Given that title, I'm assuming we can safely have a really interesting conversation around GNSS. At least that's my hope. So that's what I want to dive into in just a second. But, I mean, what does this title even mean? What do you do at Hexagon?
I'm responsible for the applied research program at Autonomy and Positioning. So, what is applied research? It's not like blue sky research, anything out there. It's applied to the areas of our business and heavily in positioning. So, what positioning capabilities are not a product that we sell today, but perhaps could be in the future? What limitations or difficulties do we have in the performance of our existing products? That's the work that my group does, trying to find better ways to do what we already do, and then new things that we could be doing that isn't a product that's sold by Hexagon today.
So we're going to get into the details of doing what you already do and the new ways of doing it later on in the conversation. But
hmm
when you say better, can you broadly classify that for us, maybe into some different groups?
Yeah,
Do you
hey.
mean better as in more precise, more accurate, quicker in every location all the time, inside, outside? What do you mean?
Yeah, actually, it's funny. My old grad supervisor, he would always, whenever somebody said better or optimal, he would say, in what way, in which parameter are you better or optimal? Because you cannot be optimal in all ways. So, yeah, better really depends on the application. So, for positioning things, that often comes down to availability. So, how often in terms of like how many epochs that you want to position are you able to have a position? And is that position of a useful accuracy? So useful accuracy, some people only need to know where they are to something like a lane width, so like 3 meters. But then maybe you need to know your position to 1 centimeter because the task that you're doing requires that. And if you don't have a 1 centimeter available position to you, it's not useful. So it's like you don't have a position anymore. So yeah, availability of the accuracy as well, maybe other parameters like pointing, orientation, attitude information could be valuable as well. And then, there's other improvements too, because first you show the capability that it's possible, and then you generally try to make that more accessible somehow. And when I say more accessible, that means getting it into a package that's like small enough that it can go in more places, or it draws less power so it can go in more places, because power isn't always just power, it's also heat sometimes. So even if you could supply with battery, sometimes you can't handle the heat, or maybe getting into a package that's lower cost, like it's less dollars so it can go in more places. So those are all the things that it could be better. Yeah, so that's what I mean by better. It depends on the particular application that you're working on, but yeah, availability and accuracy, and then the accessibility of it. How is it packaged and then accessible to the end user?
Well, I got to say, that makes a lot of sense. Not that I have a deep insight into exactly what it is that you do, but yeah, that makes a lot of sense. I'd like to start at the top, like literally at the top,
hmm
and talk about positioning. And right at the start, I mentioned GNSS. So
hmm
let's start with this broad overview there, and then work our way down to figure out other different kinds of positioning systems, or maybe and perhaps the pros and cons of some of them. So very broadly, what is GNSS?
Yeah, I noticed the first time you said GNSS, you very carefully said GNSS. And that's a problem I have often too. So I always start every presentation by saying, when I say GPS,
Yeah,
I mean
yeah,
all GNSS. It's just GPS is so much easier to say
yeah.
than
Thank you. Yep.
GNSS is. So if I say GPS, it sounds exclusive, but it isn't meant to be exclusive. It's just rolls off the tongue better. So, okay. So global navigation satellite system, and then GPS is global positioning system. So in all cases, GNSS is a state-owned constellation of satellites, state-owned and operated. GPS was the first one to go, and it's the US's constellation. They're roughly 20,000 kilometers away, and the beauty of them is all of those satellites are synchronized with each other. So it means that you, as a person on Earth here, a satellite that's in view, which means like in the sky above you, you are actually all of us are being bathed in RF in radio waves coming from those satellites, but they're very weak, and they carry a bunch of very interesting information on those signals that you can use to effectively measure the distance between you and a satellite. And if you do that to you and a total of four satellites, your four unknowns that you're solving for is your XYZ position plus the time offset of your clock and your receiver to the GPS time that's defined for all of those satellites. So if you make those four measurements, you can determine your 3D position plus your clock offset. The part that most people don't realize is the time aspect, because having that synchronized time across all of the GPS satellites allows you to turn a time measurement into a distance measurement, because speed of light times by time gives you the distance that signal traveled to get to you. So that's how it works roughly. The more satellites you have, the better, because then you have what we call redundancy in your solution. And in this case, redundancy is a very positive thing. There's other uses of the word redundancy that are not as positive. But in this case, it means you have lots of measurements, and lots of measurements allow you to minimize errors in those measurements and get a best possible solution out of it.
And this is going to sound like a really silly question, but I need to
Mm.
ask it anyway. All the different constellations of these GNSS satellites operate in the same manner. Is that correct?
Yeah, roughly in the same manner. So they're all separate. They're all separately operated and managed, but they are all very similar. GLONASS is a little bit different in that GLONASS uses multiple frequencies like within a band, and all of the other ones use the same carrier frequency for all the measurements. But they're very similar in their design. Yeah.
Okay, so why is this hard? So I'm constantly hearing about it's hard to get a great, like accurate, precise position, based on GPS, GNSS technologies, or it's
Hmm.
it's not always stable. It changes over time. Again, perhaps a silly
Mm.
question, but let's dive into this. Why is this hard? What makes this hard?
No. So let's start in like the sort of ideal conditions. So the ideal conditions are, imagine you're in the middle of the ocean or in the middle of a vast prairie. Okay. So it's just you and the sky above you. So what's hard about GNSS in that condition? So the first thing that's hard is, as I mentioned, those signals are coming from all the satellites, but they're very weak. So it actually, the GNSS signal is below the noise floor of your receiver, which means that if you don't see an obvious like spike that there's the power, that's what I'm after. So the signal processing is a bit different than what you would use in a lot of other applications, because you have to somehow fish your signal of interest out of that noise floor. So that's kind of the first hard thing about it. And then the next thing is, I guess it's not too hard. It doesn't seem that hard now. Those satellites are 20,000 kilometers away, and they don't move so quickly. And again, imagine we're in the middle of the ocean or we're in that wide open prairie. So you really have a horizon to horizon view. Today, there will be, because there is GPS, there is Galileo, there is Beidou, and there is GLONASS. If you're tracking all of those satellites, you will pretty easily see about 35 satellites at a time, like from that horizon to horizon. And each of those satellites will be providing open signals that you can make measurements on to probably three frequencies. So, yeah, three frequencies each. So, there's a lot of measurements coming in out there. So, the satellites are moving at about 3 to 7 kilometers per second, but they're very far away. So, it's actually fairly slow coming across there. But that signal is traveling 20,000 kilometers to you. So that's not a pure vacuum. Some of it is pretty close. They're pretty far out there. They're beyond the Earth's atmosphere, but it comes through the Earth's atmosphere and it's no longer a perfect vacuum, which means you now have some delay errors on the radio signal that's propagated through that. So that's an error source that you have to be concerned with. To satellite, some of the information that they're carrying on those signals is their location. So that's the ephemeris information that says where they are, because you're able to solve for your 3D position and time by distance measurements effectively to those satellites, because those satellites are at known position and a known time. But it's a broadcast ephemeris, meaning it's fairly rough because it's predicted and they're 20,000 kilometers away and they're in orbit. So it's a pretty stable orbit. But the broadcast orbits are typically at the level of some meters of accuracy, which in a lot of ways is amazing, right? That's fantastic. They're 20,000 kilometers away and you know their position to like some meters. That's great. But if you're trying to position yourself down to the centimeter, you also need to know the position of those satellites at your current epoch that you're making a measurement to that satellite to the centimeter level. Okay, so that's the satellite side. And then we were thinking of it to start with in the middle of the ocean or the middle of that prairie with a perfectly unbroken line. Like imagine you could like point your finger and it would be and ray trace it, perfect unbroken line out to that satellite 20,000 kilometers away that's moving past you at 3 to 7 kilometers per second. That's your ideal case. But what you actually have is a lot of reflections of that direct line of sight signal that you're looking for. You'll have a lot of reflections from that signal bouncing off of things around you. So if you're in that prairie out there in that pasture, there's probably not a lot that's bouncing because you've got grass and dirt around you. If you're out in the ocean, there's actually more because water is more reflective. And then imagine you wandered into civilization and you've got like buildings and structure and cars around you and hard metal surfaces and, hard stone surfaces. These are all reflections that also hit the receiver. And the receiver's job is to try to figure out where the direct line of sight signal was and all of these multipath reflections. And because they are such weak signals, you're trying to fish stuff out of the noise floor and you're integrating your measurements together to try to observe this. So that is a multipath error. And the multipath error is sort of the last error that you have, because satellite errors, propagation errors through the atmosphere, and then errors from multipath. Multipath can be mitigated partly by your antenna design, partly by your receiver design, partly by your firmware design, but there's still some left in there. And those are all of the errors that go together to affect your position where that you've computed. So what we're trying to do is correct for those things. So the orbital error, so the difference between the broadcast error and trying to get down to the centimeter level, that's precise orbits, and those are provided in correction services nowadays. The atmospheric errors can be modeled to a certain extent based on just a very basic physics model. And then there's a specific model that can happen because you say have an observing network of base stations in the area and you've at known coordinates, known fixed coordinates, and you have observed and somehow modeled and estimated the atmospheric errors, which are ionospheric and tropospheric. Troposphere is kind of nice and boring because it's just a delay and it affects the carrier and the pseudo range the same. And that, of course, changes with the amount of like water vapor in the air. So if you have like, heavy storms or anything like that. But I mean, it's an error. The signals that GNSS operates on still goes through water vapor. That's an important note about GNSS. And the ionosphere is also very interesting because the ionosphere is electromagnetic and it's actually a dispersive medium for the GNSS signal, which means it's tearing apart the code and carrier measurements. So it advances one and delays the other. And the ionosphere is really important though, because that's part of our atmosphere that protects us from like radiation coming in from the sun. And the ionosphere is governed by the sun and follows the solar cycle of the sun and is one of the most interesting errors for GNSS as well. And the ionosphere goes out to around 1,000 kilometers. It kind of moves around depending on time of year and time of day and that solar cycle. But GNSS satellites are well past that. So that ionosphere error is the other thing that you're trying to model and remove. And in a way, when you're making multiple frequency measurements at the receiver, the ionosphere has a known behavior that varies across frequencies. So if you know the ionospheric error at two frequencies, that linear slope between the two of them, you can apply to the frequencies on either side of your two observing frequencies. So if you can make measurements on two, three, or four frequencies, that's depending on how you count them, what you have available on GNSS, you can observe and remove the iono error at your receiver location and not rely so much on a broadcast iono model that you would have computed someplace else and then received over some other communication channel. Have I got all of the things for why this is hard?
You've covered a lot of them, that's for sure. I'm looking through my notes here. I'm like, yeah, tick, tick, tick. Yes. Okay. Yeah. Yes. We get it. That's very hard.
So, I mean, GPS way back in the day, it was originally developed by, it was a joint project between the Air Force and the Navy, right? So wide open spaces, right? Wide open spaces and great distances being covered. And then it's really evolved into precision uses with a lot more obstructions around you because imagine yourself, just in a regular cityscape and think of that, perfect hemisphere of, sky above you, horizon to horizon. And then think of all the things that are blocking that, perfect trace array out to where those satellites are. So yeah, it's a very, very weak signal, but it's capable of amazing precision and from over such great distances. That's the part that's amazing. So it's really great that all of these governments have decided to spend the billions of dollars that they do on this very expensive and sophisticated infrastructure out at mid Earth orbit, and then all of the ground control as well to control all of them. So,
It is actually amazing. Like when you put it like that, it is incredible that we have access to this public good, and that
yeah,
so many people, like so many governments, are prepared to invest so much in it, and then make it open. But here, I've got a sales pitch for you. Okay, I've
okay,
got a way of solving all of these problems. You ready?
sure.
Take these GNSS satellites and put them in Leo.
Yes.
Brilliant, right?
Well, I mean, why do you think it's brilliant?
Because I've seen some startups wanting to do it, and I thought, wow, I mean, clearly, if they could raise venture capital, it must be a great idea. But why don't you tear that idea apart? First, tell us what Leo is, and then destroy my dream.
So low Earth orbit. Okay, so one thing that makes it attractive to a startup is that putting a satellite into low Earth orbit is much cheaper than putting a satellite into mid Earth orbit. So low Earth orbit is more like 500 kilometers out to maybe 1,500 kilometers out, maybe 2,000. I can't remember exactly, but call it 500, 1,000. We'll just say 1,000. So 1,000 kilometers away versus 20,000 kilometers away. So one, your launch capability of what you got to do to get those satellites up there is a lot easier when you're only getting out to 1,000 kilometers. You're also still in the atmosphere of the Earth, which means you have some protection from all that radiation that's out there in space at 20,000 kilometers. So the satellites are cheaper because they don't have to be as space hardened. The other problem, though, is they're closer to the Earth, which means they'll have more disturbances in their orbit because they'll be moving, in and out based on like gravity variations of the Earth, and then they're also getting pushed on by solar flares as well. I mean, that'll happen to you further out too, but they have the gravity disturbances as well. So one, putting them in Leo is a lot more attainable. I'm sure you've probably seen stuff, right now, like people from NASA and that sort of thing talking about how Leo is kind of the domain of commercial now. And, where governmental agencies like NASA work is like the moon, Mars, Neo, Geo, because it's so much harder and so much more expensive to get out there. Okay, so that's just the practicality of it. Now, why does this make a difference to my position? Why do I care about maybe having a signal coming from Leo rather than Meo? Signal strength is one part of it. because that signal is coming to you so much closer, and you can get a stronger signal. Now, not so strong that it's going to be like cutting through like buildings, like bzzz, like it's not going to be so strong that your building is going to become transparent to that signal, but it would cut through like foliage better. So like like trees and that sort of thing, and that is definitely a help. And it may be faster to be able to acquire that signal because it's a stronger signal coming in. However, those LEOs are also moving a lot more quickly than the MEOs are. The LEOs are moving, oh, I should have this off the top of my head, but I don't. But I'll put it in another way that I do have off the top of my head. A LEO horizon to horizon will be maybe 10 minutes of visibility,
Oh,
whereas a MEO signal horizon to horizon is several hours. So, a stronger signal from a Leo, you should be able to acquire quickly, but you better acquire it more quickly because you're not going to have it in view for as long. The other benefit you get off of them is they're moving so quickly. Picture again that ray trace of the line coming from the satellite down to you on Earth. It's cutting through the atmosphere. And as it takes that, 10-minute horizon to horizon pass, it's slicing through all of those sections of the atmosphere, right? Like you just sliced an orange segment there. And the attractiveness about that is that allows you to separate some of the errors that are affecting your position from the position that it is because you're moving around. So it lets you separate your atmospheric errors that you're observing from your orbital errors, from your multipath errors, and it lets you be able to more clearly observe that atmospheric component of it and separate any of the spatially correlated errors. So it does offer a really good potential there that you would be able to have a better solution faster because you'll get more rapid observability of these errors that you need to separate and remove from the position that you're trying to solve for.
This might be. I feel like I'm asking a bunch of dumb
Mhm.
questions, but if those GNSS satellites were in LEO, could I use the near Earth orbit ones to position them, or to like ground truth their position from time to time instead of just relying on my knowledge of their orbit?
Oh, yeah. Yeah, that's a big benefit that the LEO satellites get as well. So those LEOs that are 1,000 kilometers away from Earth, they see the MEOs that are 20,000 kilometers away. So the LEOs get a really great bootstrap because they get to position themselves using GNSS. Whereas the GNSS satellites, they don't get to do that. So yeah, so right. That's actually a very good point to make is that the LEOs are their orbit could have more variation in it because they're in a kind of they're closer in, so gravity effects are going to be greater and they're in the atmosphere so they can kind of more into our atmosphere so they can kind of get jostled around a bit from that as well. But they also have more positioning capability on board them because they have GNSS receivers on them. Yeah.
Will those LEO satellites, in theory, well, not in theory, but if we ever get a constellation of them up there, will they be using the same signals, like the same frequencies as the GPS satellites do?
Yeah, that's still kind of that's I mean, it's still, oh, what did I call this? Nascent. There we go. It's still a very nascent technology that and I guess and commercialization of it is in progress. So staying in the same frequencies as GNSS has some, attractive aspects to it. One part is L band was chosen for a reason for GNSS. It's a good frequency in terms of it is not affected by water vapor very much. Whereas if you go higher frequency to like KU or KA band, if anyone's ever had satellite TV and you're someplace where like a rainstorm happens, you don't have satellite TV that afternoon. So L band was chosen for its characteristics of how well it was able to, withstand coming through our atmosphere. So that's one thing to keep in mind. The other thing is if you stay in band to L band, there's already lots of receiving equipment, antennas and receivers with RF front ends that are already kind of designed or tuned towards L band. But you'll have to figure out spectrum approvals because the radio bands like the spectrum that's used for GNSS is protected, and there's the international, coordination on that, and then there's national level on that as well. So if you want to suddenly start broadcasting a signal in band to one of the existing GNSS frequencies, oh, there is a lot of paperwork. There's a lot of paperwork that's going to need to be done, and a lot of analysis that's going to need to be done to be able to prove that you wouldn't interfere or any way harm the existing GNSS signals. So those are kind of the pros cons of staying like in the L band and then inside the GNSS bands that are already designated for GNSS. Going outside of that band, I mean, does offer other benefits and then also other disadvantages. As I mentioned, you go higher frequency. On one hand, you might be able to do a signal design that lets you deliver a bunch of data. Yeah, more data content at a higher frequency. And a higher frequency also gives you potential for some other differences in how you do your signal tracking. But then you run into the problem of you will be susceptible to water vapor, but maybe you just have so many in the sky that you won't have like a local area where the thunder cell is, but the 75% of the rest of your sky is open, so you're still fine. And then the other part of it is the receiving equipment, and what receiving equipment is available in terms of antennas and receivers that are, already kind of widely available, easily available. However, there's some interest also when you go higher. General rule of thumb is your antenna needs to be the size of it needs to be half a wavelength. So fundamental frequency of GNSS is L1 and a wavelength is 19 centimeters. So it means it's fairly difficult to have an antenna that's very good quality that's less than 8 centimeters. But if you get to shorter wavelengths, then your antenna gets smaller as well.
Right.
And then if you're looking at resiliency to things that could be disturbing your signal, the ionosphere is going to affect all of the frequencies, but it affects differently at different frequencies. So if you're much out of the L band, you might be able to do an even better observation and removal of the ionospheric effect. And then if you had some sort of jammer source as well, if you're completely out of the L band because, say, some bad actor has decided to target GNSS, and they're taken out the L band. If you're on a very different band, then you would have some good resiliency there. You'd have some good backup to it. So there's pros, cons to kind of all of the choices.
There usually is. Do you think, like, I realize we've just been talking about like taking these GNSS satellites and putting them in low Earth orbit, but do you think if we had to fundamentally, if we had the chance to redesign everything today, we're just
Mm.
like, oh, we need a global positioning system. Ooh, how are we going to do this? Satellite's a great platform. Let's do it up there. Do you think we would do what do you think we'd do differently, or would it be pretty much the same as what we've
Oh,
made?
I mean, it's as someone who's responsible for innovation, I don't really want to say, oh no, the forefathers did it perfectly. There's no possible way that could be improved upon. However, like a lot of really good thought went into that. A lot of really good thought went into that. And there was very, specific design decisions for good reasons. So the backbone of it is pretty solid. I I don't know. I mean, there's good reasons for putting it out in MEO rather than LEO, right? There's good reasons for picking L band. There's good reasons for the signal structure the way it is. There's some desire for more authentication, like more ability to be able to tell that you are tracking the true authentic signal. And that's something that, constellations like Galileo are trying to bring in because they're coming in after GPS and GLONASS and somewhat learning from what's happened before. A lot of the ways for the authentication is you have to have some sort of knowledge between the broadcasting satellite and the receiver. And GNSS, GPS especially, it has a military heritage for sure. And it's a one way system, which reduces your ability to do authentication and security, but it has a lot of really good benefits in it, like the fact that you can have an infinite number of users on the system. Because the GPS satellite, any GNSS satellite, those constellations have no clue what receivers are listening to their signal. They can't know. They broadcast in one direction. They don't receive the GNSS. They don't receive back a GNSS signal. And they have an open signal ICD. So they have an open ICD. So anyone can learn and read about the signal and receive it, which also means that it's a great target if you're trying to like do something to spoof it or jam it. But it has the benefit that the receiver gets to remain passive and never has to reveal its position to the system or even its existence to the system. And you can have an infinite number of users. So, yeah, some of the new things now are around authentication, and some of the newer systems that are positioning based on something like 5G have a two-way concept in them. And the two-way concept allows you to do a bit more exchange for authentication reasons, but it's going to bring a limit to the number of users you can have at one time. And it means that the user has to reveal themselves to actively participate with the system as well.
So now that you've dragged us down to earth, literally, when you start to talk about 5G, what about visual positioning? Would this
Mm.
is this going to be a complementary thing to GNSS, or and the reason I ask this is because I've seen some bold claims on LinkedIn recently where people are saying visual positioning is killing GPS or GNSS. This is the way of the future, kind of thing. And I couldn't help but think, wow, that's someone who's looking for attention saying that.
Yeah, I mean, it could in particular environments, like in particular use cases. So, I mean, visual positioning is really familiar to us as humans because that's what we primarily rely on, right? That's how we navigate our mostly what we base our navigation in, yeah, as humans. But I always say the goal is to be not just match the human, but to be better than the human. And the thing with GNSS is it's the only thing out there that gives you a measure of where you are absolute, like on the surface of the earth. I think we've all had the experience of maybe traveling too much and waking up in the middle of the night and not being able to figure out where you are for some seconds. And you've opened up your eyes and you're like looking around your dark hotel room and like you're literally you can feel the search function going in your head trying to correlate what your eyes are seeing to what your mental map of like known sleeping locations is. So that's the thing with visual positioning is it shows you your immediate surroundings very well and it lets you move through your immediate environment in a way that keeps you from like running into things, right? You aren't going to hit anything, but it needs to be tied to some kind of bigger picture absolute reference to put that in context. And we as humans have like our map and that's why a landmark is a landmark because we recognize the landmark and we know where that is in that larger, area map that lives in our head. Visual positioning needs to do the same thing. Visual positioning has to be tied to like a database of known coordinates, like from something recognizable in the scene. And it also, so it works really well if you're, in a busy city street, just the way we would navigate nicely, because a busy city street is full of structure, right? It's full of structure. There's buildings, there's signposts, there's that sort of thing. All of the things that make it hard to receive GNSS signals because you've got tall buildings on either side of you. But that's all the structure that's really useful for your visual positioning. Whereas if you were in the middle of that ocean we were talking about, or the middle of the prairie, visual positioning doesn't help you as much. If all you have around for features are, ocean waves, you're not. That becomes a lot more difficult to position yourself. So it definitely has its place and it's definitely augmented or not even, I should say, enabled by the fact that we have the ability to create beautiful reference databases of known coordinates and, often existing maps or existing imagery of the area that we're in, but is most useful in that very immediate surroundings local navigation sense. Not as useful, not it has to be tied to some larger reference in that big picture absolute sense. And the other part of it is the time aspect that I mentioned. The really sneaky part about GNSS is it gives you a time reference that is like having a rubidium or cesium clock, which is really expensive and a really lousy package for anyone to actually use. And even those visual positioning systems need a master clock someplace and a time reference from someplace. And that generally comes from GPS, GNSS.
It sounds like what we're talking about when we talk about these two technologies is one like visual positioning. Don't run into stuff.
Hmm.
And the other one is this is where you are relative to the surface of the earth.
Yeah, and GPS, that's the part that it misses, or GNSS that it misses is the local context, right?
Yeah.
Just because you know your coordinate doesn't mean you're not lost.
Yeah. Yeah.
So GPS kind of works in this like if you think about it, it's this perfect geodetic world where it's just, like, drawings on like drawings from your physics class, on a whiteboard. And then visual positioning is like, oh yeah, and this is all the real stuff that's around you, right? Visual positioning is what lets you see the obstacle you're about to run into, or it maybe does a recognition on like some sort of known landmark, like a signpost or something like that. And GPS, GNSS can't give you that local contextual information. It gives you the coordinate. But now you need to put that into some kind of meaningful context for you. Yeah.
Right. Yeah. So we're talking about two technologies which are more complementary than competitive.
Yeah, yeah. I mean, what this is saying, different horses for different courses.
Yeah.
They both have their environments that they're very strong in, and they both have their environments that they're weak in. Because, I mean, visual positioning, I mean, we've all, your eyes can fool you. There's optical illusions. It can be too bright. It can be too dark. Those type of things, I guess, are the ionospheric error and multipath of visual positioning. But what I mean is it's different error sources on each of them, which means, yeah, they're very complementary and they have their strong environments and they have their weak environments.
When you think about networks down here on the ground, like what ways of positioning
Hmm.
things down here on the ground, is there any sort of strong competitors to GNSS that you can think of?
Oh, for terrestrial based positioning?
Yeah.
Yeah, I mean, it depends what level of accuracy you're trying to achieve out of it. Again, so like Wi-Fi positioning is really common, and it's integrated into your cell phone and the blue dot that everyone is used to following. Wi-Fi is, well, usually it's a two-way, but it could be a one-way as well. It's not as precise, and it's also in a lot of ways not as secure because again, to be able to position yourself to that transmitting source, you need to know the position of the transmitting source pretty well. And because Wi-Fi is very decentralized, anybody can throw up like an access point. It really depends on if they followed a protocol and entered in a coordinate properly, or if that coordinate has been somehow like derived or observed. So, okay, that's Wi-Fi is pretty common. It's good for the contextual kind of like get you in the right like city block, maybe into the right building kind of thing. But it doesn't quite compete with GNSS in terms. No way does it in terms of precision and accuracy, but it might in availability again if you're in that like very urban kind of situation. I mentioned 5G earlier. 5G has in their signal design plans for pretty good positioning capability with some advantages over GNSS in that it is capable of doing an angle of arrival measurement. So for any surveyors listening, it means that it's like a bearing distance problem rather than a resection problem. It means that you can say, like, I know that thing is at that heading and it's that many meters away. So you can get a very rough approximation off of only one measurement like that. But then why 5G has the disadvantage of a little bit slow to roll out right now, a
Yeah.
little bit slow to roll out. And then you can't access it well unless you're a member of the network. So the positioning capability is not done on the device, it's done at the mobile network operator.
Huh.
So that's kind of an interesting thing too, because it means it's all in the hands of the network operator. And a lot of us thinking about, ubiquitous positioning are used to a GPS type of styling where the system isn't aware of the user and the user doesn't have to interact with the system. With 5G, you have to be part of that network to be able to access the positioning capability of it.
But I think we're also used to the positioning being calculated on the device at the edge of the network as opposed to,
Hmm.
at a central location within the network.
Yeah. Yeah.
That's interesting. Are there any sort of radio-based networks, radio-based ranging to? Uh,
Yeah, there's lots of local ones that are done, for a particular install someplace that it's the same principle. You've got a transmitter at a known location and you've got it's transmitting a signal that you're able to make at least a rough distance or code measurement off of it and probably a carrier phase measurement for precision as well. That's how ultra wideband systems work. There's some that use a very GNSS like signal as well that are sort of, oh, they used to be called pseudolights, but they call them a lot of different things now because I think pseudolights didn't really fly when they first got introduced. So they needed a rebranding. And the difficulty with that is it's infrastructure that has to be installed and maintained by someone. And it's who's going to bear the cost to
yeah,
install
yeah,
and maintain that, and then what is the protocol? What's the signal interface that you have to know to interface with it? So there's lots of things that are set up for like indoor positioning in like a warehouse or in a local area that might not be indoor, but like a mine environment that happens too. But they're private, basically. They're proprietary. They're set up for somebody's specific use case, and they're operating like this is my space, this is what I'm controlling here. And the difficulty has been for like a general public use thing is who maintains installs the infrastructure and how do you get access to the signal.
yeah, yeah. And is it what standard, or are they using a standard? Does it make sense for me to invest time in decoding this and figuring out how it works if I can only use it here?
Right, right. And then standards be slow, right? That's the issue with them. They're great in that everybody can do it, but the first kind of wave of it is usually proprietary because somebody has a specific problem that they want to solve. And then it's the further on waves when things are more mature that you get to the point where standardization has happened and you can go between different instances of it, like what you've seen with for all the old people, like, mobile phones. It used to be you had to have one phone for North America and a different phone for Europe. It used to be that, if the carriers didn't have agreements with each other. So if you wandered out of service with your carrier, you didn't have service, but now most of them have agreements, right? That when you wander out, it'll pick up someplace else. That just takes a bit of time to come. So for the terrestrial based stuff, that is, yeah, a little bit probably market forces to see if there's enough of those like proprietary specific local area things that proliferate with enough users that would be moving in between those networks that there gets to be a real sort of momentum and demand for it.
Yeah, that makes a lot of sense. Well, we've come a long way. Now it's time to talk about the future, but this is not going to be a
Mm,
problem for you because if I recall right, you're the VP of Innovation, right?
yeah.
Great. So what does the future of all this look like? What can we expect to see in terms of amazing innovation in, we can start with GNSS if you want, if you've got something to say there, or we can look at positioning in a broader sense.
Yeah, I mean, I think the future is really getting to a point of seamless combination of all the different positioning technologies to take you through the different environments that you're, trying to operate in. So, we talked about the visual positioning. Yeah, it's really intuitive and it makes a lot of sense. But, the supporting enabling technology that goes with that is those reference maps and those databases of known coordinates, and how do you access those in real time on the edge on your device. And I don't think GNSS is going away, but it can definitely be augmented, and it's a really useful sensor because actually it doesn't require calibration, which is what every other sensor requires, is calibration. So I think it's especially for navigation or positioning in sort of a civilization sense. So meaning you're in a city, you have connectivity, you're in surroundings that are somehow there. When I say they're familiar to you, I mean it's because they've been pre-mapped, right? They're pre-mapped. You've got that reference from someplace. That combination of all those things together and that being, I guess, attainable without like a hideous amount of like setup and bugginess is probably the future for it, which doesn't sound like that amazing, but to get all of the details of the things working together seamlessly, it is actually fairly amazing.
Yeah, well, to me, it sounds amazing. Is this a case of like the better you get, the harder it is to get better? And we've already got something that's pretty great. We've got this pretty amazing foundation.
For sure. And it's
Yeah,
free,
yeah,
right? GNSS, like, I mean, it's not free. The taxpayers are supporting
yeah,
it. But no, nobody individually has to like pay a fee for using GNSS. So it is really hard to beat in the areas that it serves well, but it doesn't serve a lot of areas well. Like, oh, I'm in a city, right? I don't have a good clear view of the sky. I have lots of obstructions, or, oh, I went indoors, or maybe I'm some kind of vehicle that has to do an indoor outdoor job and I need to go like into I'm unloading like cargo, like I'm logistics, right? And I'm taking something off of the truck and I'm moving into the warehouse and I'm moving back out. That seamlessness of in and out is difficult to bridge right now for, if you're trying to like buy a system to like install on a vehicle. So, yeah, that's the part. GNSS does not work everywhere, but it works real well in a lot of places. And I think it'll always be used there, but it's being able to make it really truly ubiquitous positioning that you can position to the centimeter if you need to. But then that's the other part, is who needs to? Who needs to know their position for a centimeter? But if you're a machine, if you're a little robot,
yeah.
that starts to have a lot more applications. If you're a small sort of last mile kind of robot or a warehouse kind of robot, then the centimeter level positioning becomes a lot more important.
Exactly. Especially if you're a last mile robot, a small robot, and you're having anything to do with humans.
Mm.
I think
Mhm.
then it's going to be really, really important to have a combination of these sensors and systems and to be able to use them all to augment each other and figure out like not only where I am in the grand scheme of things, where I am in a very local sense, also within a house, within a building,
Mhm.
within some other built environment, but where am I with regards to the humans, the soft objects around me?
Yeah, and that's actually interesting because you have kind of you have a bit of a bit of an inverse problem there, because we talk about reality capture often, and reality capture has the goal of capturing the fixed infrastructure, and the map shows you your fixed non-moving objects. But when you're trying to navigate in real time, you really care deeply about the ephemeral moving objects, because those are like the people and the pets and the other things. So it's funny in that when you're doing reality capture, the moving things are often your noise that you don't care about. But when you're navigating, they're the thing that you most immediately care about.
Yeah, that's a really, really good point.
Yeah.
So we've talked broadly about this thing. Is there any one thing out of all of our discussion so far that you're most excited about? You think, I want to see that implemented, or I am excited about this technology or this piece of tech.
Oh, I can't pick just one.
You have to.
Oh, I should have thought of this before. Just one, hey? Well, in some ways, maybe it goes back to my beginnings, like my kind of origin in this. I think it'd be like the one thing that most surprises me today when I look back to like 10 years ago is that space is a real legitimate like topic now. It's not just Star Trek anymore. And the idea of more space-based RF, like more space-based RF navigation, like those LEOs that we were talking about, is fascinating, that could actually happen. And then if we end up with that amount of like stuff in orbit as well, positioning on orbit is also going to become totally different than it is today. Do you remember that Wally movie from like 2008?
Yeah,
Yeah, it
loved it. Yep,
it's
yep,
kind of like, yeah, but do you remember the shot of like, Earth, and it had this like really like, dirty cloud of junk all around the outside of it?
yep. Yeah, I do.
Yeah, that's kind of what we might be heading towards. So if you have all of that stuff in orbit, the positioning and perception requirements for, trying to operate in low Earth orbit are going to be really fascinating because you're moving so fast.
Yeah. Yeah.
Yeah.
I'm actually in talks with a company. I want to do a podcast episode with them, and they are positioning things in space. So
Mhm.
my sort of I haven't had a good chance, like a chance to sit down with them yet and really understand what they do. But my rough understanding is they have synthetic aperture radar or radars
Sure.
pointed
Yeah.
up at space, and they're
Yeah.
mapping things up there and positioning them,
Yeah.
which is really interesting because it's like you're saying, it's getting busy up there.
Yeah, and I mean, I grew up watching Star Trek. I grew up watching Star Trek, the old reruns that were on right before supper with the original Star Trek, and then Next Generation Star Trek was like the new Star Trek when I was a teenager. And it felt like we didn't really make much progress towards that, vision of Star Trek, like from the time I was a teenager until like recently. And it's like, oh, that could be a thing.
That could be a thing. Hey, so you're really passionate about positioning, and you know a ton about it. Do you feel like it gets lost in the context when people talk about, some of the other stuff that's happening in, like, if you think about the geospatial world? For me, I think this is a fascinating topic, but I feel like it gets a bit lost in between, like, the computer vision and new space and imaging technologies, especially imaging technologies and the AI that we're using to resolve features within images and collect data and all these other
Hmm.
things. I feel like positioning is kind of very important, but I feel like it's lost, or maybe not enough as attention is being paid to it.
Oh, it's the thing that's always overlooked. It's the fundamental in every physics problem you ever had. It's the given quantity. It's always assumed that it's there, and of course it's there. And then, oh, but when it's not, what happens? And I think a lot of, around the vision and the machine learning aspect of it, it's intuitive, right? Like it's something somebody can understand because it's implicit. It's what we do every day implicitly. Whereas positioning via GNSS or inertial, it's math. It's a bunch of math and estimation that you need to learn, and it's not intuitive and it's not obvious like that. But it's really computationally light compared to what computer vision is. Very computationally light. And it's also, and this, oh, if you're an estimation person, this has so many different meanings in it. But anyway, it's also really unbiased because it's not dependent on what training data that you used. And it's never going to get confused by a human wearing a skirt as opposed to a human wearing pants as to whether or not that's a human. So it's very, very computationally efficient and it offers a capability that humans don't have. Whereas everything to do with computer vision and AI is merely emulating what our meat circuits and eyeballs do for ourselves every day.
Meat circuits and eyeballs. That's got to be the quote of the conversation. I want to throw something else at you. I think it gets overlooked because people think, haven't we done this already? Like, isn't it
Oh,
done? Why
yeah.
why would I focus on
Oh,
that?
for sure. That was me in the year 2000. Me in the year 2000, when I was trying to decide what to do my grad studies in, I was like, I do not want to do it on GPS because that is so done.
Yeah.
So I focused on inertial navigation instead, which is actually kind of funny because inertial navigation started before GPS.
Well,
But yeah, in some ways it does feel like it's done, but it's done in some conditions, but not all conditions. And what's not done is the seamlessness of switching between different systems, like different technologies, and making it work in all of the conditions seamlessly. Yeah.
Sandy, this feels like a really good place to sort of wind up the conversation. And I just want to say thanks. Like the first time we spoke was amazing, really enjoyed it. And I've equally enjoyed this conversation. So I really
Ah,
appreciate your time. It's been
thank you
great.
very much. I enjoyed talking to you too, and maybe we'll meet in person someday.
I would really like that. Maybe we'll end up in the same conference in Calgary or Banff next year. Who knows?
Yeah, or Banff. Yeah, it's a good choice.
In the meantime, there'll be a bunch of people listening to this thinking, how can I reach
Hmm.
out to this person? Is there anywhere they can go to do that?
Oh, would you reach out to me?
Yeah.
Oh, well, I'm on LinkedIn, so I'm
Yeah.
pretty easy to find on LinkedIn.
Okay. I'll put a link to your profile in the episodes in the show notes of this episode. So yeah, people want they can catch up with you. Thanks again for your time.
Perfect.
Really enjoyed
Thank
it.
you.
Cheers.
All right. Bye.
Well, I really hope you enjoyed that episode with Sandy Kennedy, Vice President of Innovation in Autonomy and Positioning at Hexagon. I'll put a link to her LinkedIn profile in the show notes of this episode, and I'll also link to other relevant episodes in the show notes today. Okay, that's it for me. That's it for this week's episode of the Mapscaping Podcast. I'll be back again soon. I hope that you'll join me then.